Hi everybody, this is Austin Hoggett here to give you another lecture from OpenStack's Intermediate Algebra. Today's section is going to be talking about the square root property, which is allowing us to solve particular quadratic equations given the two forms that you see here. Let's take a look at the first examples. In cases we've seen these types of equations before, we try to follow the factoring and zero product rule methods to get to our solutions. Factoring using different special product rules, reversing the distribution, and allowing us to identify how to apply the zero product rule was how we found solutions to equations like this. And you'll notice I have in this example something like x squared is equal to 9. The question could be posed, what value, when we square it, is equal to 9? And of course, thinking on that for a moment, we could probably come up with the answers without struggling too much. X equals 3 and negative 3. There's another method, however, that we can use. The square root property allows us to take this expression and use radicals to undo the exponentiation. So x squared is equal to 9 can be solved by taking the square root of each side of this expression. We've talked about before what's called the principal root of an expression. Something like the square root of 9, for instance, actually has two solutions, as we would expect based on our second technique. The square root of x squared, again, can be answered using the definition of the root. What raised to the second power gives me x squared? When we simplify in each case, we get x, and on the right-hand side, we actually have our solution plus or minus 9. It becomes important when we start using the square root property to consider that we do actually have to impose this plus or minus symbol. Here's another example where we're asked to solve the equation 2x squared is equal to 98. This again could be solved by factoring and applying the zero product rule. But you'll notice in these cases that it's actually quite easy to use the square root property as well. Just like when we talked about solving radical equations, we want to start by isolating the term that's being exponentiated here. By division here, I can get the square term by itself, so x squared must be equal to 49. In this case, again, I can pause and think about the question in this way. What number, when I raise it to the second power, is equal to 49? There should be two solutions in this case. Again, because of my exponent here, it suggests that the degree of this equation is a second degree. By, again, taking the square root of each side, I'm imposing potentially two solutions, both the positive and negative solutions to that square root on the right-hand side. So we do, in fact, get plus or minus 7 for our two answers. In this case, notice that my expressions start on the same side. I cannot actually apply the factoring and zero product rule in this case because it doesn't follow any of those special patterns that we've seen before. So in this instance, what we'll start with is, again, trying to isolate the term that is being squared. Moving my constant to the other side by subtraction here, I get something like x squared is equal to negative 72. This implies that when I take the square root of each side, I'm going to have the square root of some type of negative number. While this is what is necessary to solve the equation, it also implies that we're going to end up with an imaginary value for the solution. When we take the square root of each side, sure enough, as before, we have to consider that it's going to give me both a positive and negative answer. And of course, the imaginary unit can be removed to make this expression turn to positive square root of 72. Continuing, though, to simplify that square root requires that we, again, break it apart into two pieces. We want to identify the perfect square factor and non-perfect square factor in that expression. So for 72, my perfect square is going to be 36. My non-perfect square factor is 2. Applying the product rule allows me to split those into their own roots. And so I get something like the square root of 36 times the square root of 2. Simplifying allows me to get my solution here of x is equal to plus or minus 6i square root of 2. It's quite a complicated looking answer, and of course, it takes lots of effort to think about the process here from a general strategy standpoint. I'm given the equation initially in the form of a quadratic set equal to 0. But the factoring techniques that we've talked about before, either the AC method or some of our special product rules, are insufficient to get to a result. So, practicing identifying the correct technique given any particular problem is critical for being successful. You'll notice that in this case, there's no middle term that matches to what we would distinguish as a quadratic. Typically, they come in the form ax squared plus bx plus c is equal to 0, or perhaps something more precise like a difference of squares. We're not always guaranteed that these particular forms will show up, but of course it makes it a lot easier to use and identify the factoring techniques necessary to get to a solution. We'll take out another example where we might need to rearrange the equation first. Here I have 2/3 times u squared plus 5 is equal to 17. I would start in this case by suggesting we move our constants to the same side. I can accomplish that in this instance by subtraction. We're left now with something like 2/3 u squared is equal to 12. I haven't quite fully isolated my square term by doing this just yet. I still have a coefficient that is a fraction. We could either divide each side by 2/3, but if you recall your computations with fractions, you'll recall that multiplying by the reciprocal and division by fraction are really the same process. So I can remove the coefficient here by finding the product. We get u squared is equal to 18. And just like before, we'll take now our expression u squared is equal to 18 and simplify by taking the square root of each side. Square root of u squared is just going to give me the base value u, and we get plus or minus square root 9 times square root 2 when we separate the square root of 18 into its perfect square and non-perfect square factors. Square root of 9 is going to give me plus or minus 3 times our non-perfect square, square root of 2. So here's our solution finally to this crazy looking question. Let's look at another example where the square term is a binomial. A lot of students will be tempted in this case to actually find the product of something like y minus 7 squared first. If we were to do that, we'd also have to multiply everything by 4, and so the task here can be quite a challenge. Either by the FOIL method or some other version of it, we could multiply through here and discover we get quite a complicated expression, y squared minus 14y plus 49, all multiplied by 4. So I wouldn't necessarily recommend it in this case because this task now is that much more difficult. If I set that expression equal to 48, for instance, we may say by division here, this reduces to a trinomial of sorts that we can set equal to 0 and solve by factoring. But frankly, this is a lot of work for not a lot of output. Moving our constants to the same side, we would then have to identify the factors of our last term here. That add up to negative 14. Since the factors of 37 are 1 and 37, this is not going to be a viable option. So you can waste a lot of time and effort trying to factor a problem like this, even after you've attempted to create a trinomial of sorts. So again, factoring and applying the zero product rule may seem like a good idea in this case because it seems as though we have some kind of trinomial, but this is a thwarted effort at the end. Our trinomial can be solved in another way, however. Instead, we could divide each side by 4 to eliminate that coefficient, still leaving me with my square term intact. Now we can apply the square root property to eliminate the square term in each case. I'm left with the binomial y minus 7, and the square root of 12 reduces to give me plus or minus 2 square root of 3. The last step is to move constants to the same side. What makes this task seem a bit odd is adding a whole number value to a sort of complicated looking expression. Since 7 is just a numeric value and 2 square root of 3 is an irrational number, we can't really combine these together any further. We still end up with two solutions, as you might expect, given that this is a trinomial of a second degree term. Since our two solutions are going to be 7 plus 2 square root of 3 and 7 minus 2 square root of 3, you may see them written out more explicitly in separate statements. In most cases, I'll leave them combined like this just for succinct writing purposes. Here's another example, again, where we need to consider that division by 2 is more critical than multiplication by everything on the left-hand side. In the interest of saving time, we would isolate our square term so that we can apply this square root property. Taking the square root now of each side, I get something like b plus 2 on the left-hand side of the equation, whereas the square root of 40 here can be simplified by separating out our perfect squares and non-perfect square factors. In this case, we get the square root of 4 times 10. That would simplify to give me the square root of 4 times the square root of 10. Simplifying even further, we get 2 square root of 10. And lastly, moving our constant to the other side gives me a solution of b is equal to negative 2 plus or minus 2 square root of 10. So again, identifying the perfect square factors is critical in this case. Not only do you have to know how to apply this square root property to properly solve the equation, but the simplification of all these roots becomes critical. Recognizing that because our particular problem has an exponent of 2, and therefore there should be two solutions, the plus or minus shouldn't throw you off too much. And the biggest indicator, again, I can give you is the degree of the expression indicating how many solutions you should have. If you're leaving off the positive and negative solutions when you import that square root property into the problem solving process, you're going to be missing at least one of your solutions. Let's continue with some more examples. In this case, again, I've luckily already got what I need isolated, my square term, and it's set equal to some fraction like this. We can immediately apply the square root property and take the root of each side. One thing to keep in mind in this case is that I'm not going to be simplifying using the product rule on the right-hand side. I need to use the quotient rule. So while the exponent and radical cancel each other out on the left-hand side, leaving me with x minus 1/3, on the right-hand side, I'm going to have plus or minus whatever the square root of 5/9 would be. Again, we can separate this using the quotient rule into two parts. Square root of 9 in the denominator, square root of 5 in the numerator. Simplifying this expression would mean leaving the numerator as is, but reducing the square root of 9 to 3. Now we can move our constants to the same side, leaving me with a solution here of 1/3 plus or minus square root 5 over 3. You may also see this written slightly differently. Since my denominator for each of the expressions here is 3, we could also write it in the following format. So again, this plus or minus is meant to indicate the two solutions. We could either write them out explicitly, 1/3 plus square root 5 over 3, and 1/3 minus square root 5 over 3. Here's another example. We're asked to identify again the solutions here. We'll start by moving our constants to the same side. Again, we want to isolate that term which is being squared. So by subtraction here, we get 2 times x minus 2 squared is equal to 54. We can divide each side now by that coefficient to simplify further. This leaves me with x minus 2 raised to the second, which must be equal to 27. The square root property can be applied now. As we take the square root of each side, our expression simplifies to give me x minus 2, and that will be equal to plus or minus the square root of 27. 27 has perfect square factors of 9 and non-perfect square factors of 3, which reduces the expression to plus or minus 3 square root of 3. Moving my constants to the same side, we finish the problem and get our two solutions. X is equal to 2 plus 3 square root of 3, and 2 minus square root of 3 times 3. So again, we need to start always by isolating the term that's being squared so that we can apply this product rule or quotient rule on our way to simplifying the expressions. Let's take a look at one other example. In this case, I've already got my square term isolated, so again, I can apply my square property immediately. We're always trying to match our index of the root to whatever expression is being given. So if your exponent happens to be larger, then we'll change the type of root that we're going to use. In all these examples, we've seen squares, and so the root we use is the square root. But if I have a cube term or a fourth or fifth exponent term, I'll use a different root. Again, our square term's already isolated, so using the square root property, I can simplify the left-hand side to being just the base, 2x minus 3. On the right-hand side, I'm taking the square root of a negative number, which again should be positive and negative. Removing the imaginary part allows me to simplify further with the square root of 12. In this case, the square root of 12 can be separated into two parts. Square root of 4, which reduces to 2, and the square root of 3, our non-perfect square factor. We've got a few more steps in this case to isolate our variable all the way. By moving the constant to the same side here, we end up with the expression 2x equals 3 plus or minus 2I square root of 3. Lastly, we can divide by our coefficient to get the solution you see here. And again, we could write this in a couple different formats. In this instance, because our expression is likely going to be presented in one concise statement like this, it's just easier to write it out that way, but we may also write it as 3 halves plus or minus 2I square root of 3 over 2. And when we write it in this way, you'll notice that there is at least one factor that can be reduced. In other words, we could rewrite the expression now as 3 halves plus or minus I square root of 3. The two values here will cancel each other out, reducing to the expression you see here.